have for Colóquio today Professor Steve Meech from Anglia University. Ismail is going to give a more formal presentation.
Yeah, it's a huge pleasure to have Steve Meech here today. So, Steve Meech is a professor of chemistry at the University of Anglia in the UK. Steve started his PhD in Southampton and then finished it at the Royal Institution in London because his supervisor had moved there in the early 80s, and it was David Phillips. So the Royal Institution is, I think everyone knows, was the place for Michael Faraday to did his career. And just a side note as a curiosity, when Steve was doing his PhD there, one day Margaret Thatcher was supposed to go there to visit the place, and Steve's supervisor asked him if on that day he could stay at home, not so. You can imagine why that was the case. Well, okay, so after finishing his PhD, he had an European fellowship where he spent some time in Groningen in the Netherlands. And then he became a lecturer at Heriot Watt University in Scotland. And during this time, he got another fellowship, Inoue Fellowship, to spend some time in Japan. And then in 1994, he moved to the University of Anglia, so it's 30 years this year. And there he established a highly successful group of ultrafast spectroscopy, so he got multi-million-pound awards where he then built really great infrastructure, supervised many students, postdocs, which moved on, and many of them are leaders in the field worldwide today. So Steve has been publishing highly cited papers in all the main journals like Science, Nature, JACS, PRL. He has written many reviews and book chapters. He has also been coordinator and has been participating in all the main conferences of the area, and has been editor of the Journal of Photochemistry and Photobiology, where he's now actually an emeritus. So over the years, Steve has been a supervisor, colleague, collaborator, and above all, a good friend. So he has donated equipment to the institute here, which is worth hundreds of thousands of reais. So we are very grateful to him and grateful that you can be here and give the talk for us today. Thank you.
Okay, well, thank you, Ismail, for the introduction. And it really is great to be here to see where Ismail is working, finally. It's my first time in Brazil, so I'm having a great time, enjoying it very much. I thought I'd just start with a short introduction as to where Norwich is, since it's not the most famous city in the United Kingdom. It's known, if people know it at all, they know it because of we once had a Premier League football team, but sadly they're no longer in the Premier League, so it's become obscure again. So here we are, just on the reason few people know the city is because you wouldn't go there accidentally, right? There's nothing. We're surrounded by the North Sea there, so it's most of our neighbours are fish, essentially. But it's a nice university on a green campus, built in the 1960s. So built from concrete in the 1960s, now partly falling down, but nevertheless, from the air at least, it looks attractive. And it's a nice old city as well. So if you have a chance to visit, please do drop me a line, and I'll be happy to show you around. Ultrafast spectroscopy is what we do in my group there. Actually, we have several different. We're interested in the techniques, and so we just try to apply them to different things which are of interest to us. And there are three basic areas we work in. Fluorescent and photoactive proteins, so basically photobiology is one of our areas. Photophysics, in particular with regard to molecular switches and motors, is another thing we're active in. And if anyone's interested in those, then I'm around for the next couple of days, and I'm happy to talk about those subjects. But what I'm going to focus on today is this one here. This is multi-dimensional spectroscopy of molecular diamonds. We've been working on several molecular diamonds over the years, and I'm sort of trying to bring it together into a new topic. This is actually a new talk that I'll be preparing. So this is going to be the title: Ultrafast Photophysics in Molecular Diamonds. Why? Why would we be interested in molecular diamonds? It turns out that they're useful in many respects. For example, here's a dimer, classical ruthenium complex, redox complex, but not very good absorbing in the ultraviolet region of the spectrum. If you make dimers or multimers, in this case, by attaching this carbazole-like group here, then this can absorb light and transfer energy into here. So you've got an antenna to more efficiently harvest solar energy for solar energy conversion. So this is one of the goals of studying photophysics in dimers. Singlet fission is another topic which is attracting a great deal of interest recently. Again, this is for energy research for photovoltaics. Essentially, it's nice to have a triplet excitation for photoconversion, because triplets live for a long time. But usually, if you have one photon, you put it into a sensitizer, the sensitizer transfers its energy to the triplet state, so one photon in, one electron out, this provided the electron can be got from here. The nice thing about singlet fission is that it occurs in these strongly coupled dimer structures, usually between pentasemes. It doesn't have to be pentaseme, but usually it is. And the neat thing here is this absorbs one photon in the visible region of the spectrum. And that can undergo, because of the coupling between the dimers here, that can undergo what's called singlet fission and give you two triplet excitations. And that means that in principle, you've got one photon in and two electrons out. So in principle, I keep using that word, in principle, you can have in excess of 100% efficiency in your photovoltaic devices. And there are some reports of that 140% efficiency in the literature that have not been repeated as far as I'm aware. But nevertheless, this process certainly occurs, and it's attracting a lot of attention. So this is one of, and it's a unique thing associated with strongly coupled dimers. This is another topic, unusual thing that dimers composed of identical halves do. You would think that that would always be a neutral molecule, right, by symmetry. And yet it turns out, on a very fast timescale, once this absorbs a photon, it can convert rapidly to this, what is essentially a charge-separated state. And that, again, is potentially useful in photovoltaics because part of the charge separation has already happened, so all you have to do is get an electron transfer reaction here, and you've got two free charges. So, potentially a useful route. And finally, this is one I've added because I've just been at a meeting where they're talking about quantum information science, and many of the proposed sources of entanglement, for example, involve spins, which can be populated in many cases by electron transfer reactions. And if you have these longer dimers, then those spins can be separated. And that's important if you want to use these so-called molecular qubits. So there are lots of potential applications for photochemistry and photophysics in molecular diamonds. And is what we're trying to do is understand what's the basic nature of the photophysics in general molecular diamonds. So that's really why we're going in this direction. I thought I'd try to introduce the basic concepts of what happens in molecular diamonds. As you've already seen, these can involve some, what I'm sure to most people in this audience will look like quite complicated molecules. So, and we'll be talking about those at length, but I'm a chemist, but even to me, some of those molecules look quite complicated. So we can do, are you familiar with the spherical cow approximation? You can take this and you can say, yeah, okay, it's very complicated, but we can reduce it to that. Well, in this case, the spherical cow approximation is that if you get lost along the way, you can always think of these dimers as simply being two coupled dipoles. And you can combine those dipoles together in an out-of-phase or an in-phase fashion. If you do that, you get two states formed. Okay, so these are the exotonically coupled dimers that I'll be talking about. And if you have them stacked right on top of one another, then this becomes what we call an H dimer. In that case, the higher energy of these two new transitions, exotonically coupled pair, is the one which is optically allowed, and the lower energy one is optically forbidden. So what you see in this case is if you go from a monomer to form a dimer, then that will correspond to a blue shift, and the emission will disappear. Other things can happen after that, but that's the basics of what happens in these H dimers. You can change the structure slightly, still keeping them linear with one another, but if you slide them along, then that's changing this angle theta here. And as that goes through 54.7 degrees, sometimes with the magic angle, then you swap over, and the in-phase combination becomes the lowest energy state, and the outer-phase, the forbidden one, becomes the higher energy state. And then you undergo a redshift, but you retain the emission, and we refer to these as J-type dimers. Mostly I'll be talking about H-type dimers in this talk. This was all worked out a long time ago in for chemists in a beautiful paper by Kasha, and so we refer to this as Kasha's rule. In physics, there's something very similar called the Davidoff splitting, which it may be more familiar to people from a solid state background. But it's essentially a dipole-dipole coupling, shown here. Depends strongly on the distance and the angles. Of course, as we bring these, this is quite a long-range interaction, but as we bring these closer and closer together, then you start to have to worry about the wave function overlap, and then the spherical Cow approximation starts to break down. And because then the wave function overlap is going to be specific to the kind of molecule that comprises the dimers. But it's important because when you have the close approach of the two, then you can get charge exchange between the two halves of the dimer. And so this charge transfer coupling becomes significant. And you can see these are both calculated, so this is the Coulombic coupling shown here as a function of the angle alpha and theta for a fixed distance. And this is the Coulombic coupling, here shown as a function of distance. So beyond about 5 angstroms, the wave function overlap doesn't occur, so it's not an important thing. But then as the approach becomes closer, it becomes more significant, and it's actually quite strongly dependent upon the geometry, particularly the twisting of one dimer with respect to the other. Okay, so that's the short-range interaction. Depends upon the wave function overlap, and these two things can have the same sign, they can reinforce, or they can have the opposite sign, and they can oppose one another. So it's possible, actually, to have the two cancel one another out. You can have something which is actually strongly coupled, but in fact looks like a monomer. So, just makes life a little bit more complicated. Okay, so these interdimer couplings can then lead to all kinds of different states, and is what we want to do. What our job is, essentially, as chemists and spectroscopists, is to understand and control which of these states we're going into, because they all have different photophysics and different excited state behavior. So the pure exciton state is just where we have a pair of identical molecules making up a dimer. Therefore, we can't know which side has got the excitation. So it's delocalized excitation, and this gives us our Kasha-type coupling. However, if we have this wave function overlap, then we can have this charge exchange going on here. This still, provided these two should exactly balance one another, so the molecule still remains overall neutral, but nevertheless, this interaction has an effect on the spectrum, and I'll refer to that as forming an excimer. So we'll have a weakly emitting excimer system formed here. But surprisingly, you have this, or maybe not so surprisingly, but this structure exists. If B becomes large, then this becomes an important term. And you can imagine if you put that into an electric field, and you align it with an electric field, then it would be possible to favour one half over the other. So you end up with actually just one of them dominating, and that then becomes your charge separating state. We don't, and I'm not going to in this talk, deliberately apply an electric field to these things, but of course we have a polar solvent surrounding these, and it's possible for structural changes in that solvent, fluctuations in the solvent environment, to actually drive this charge separation, and I'll show you an example of that. And then shown here, this is coming from the excimer state, or the exciton state here. This can undergo intersystem crossing in what's a spin-allowed process, because we can, if we have two triplets, then we can form a singlet state from that. And then that singlet state can dissociate into our two separate triplets, and this is the case of singlet fission. So in many cases, or many people are putting a lot of effort synthetically into producing systems in which this process is energetically favorable, because then you can supposedly have more than 100% efficiency in photovoltaics. Okay, so our objective is to understand and find means of controlling how these light-driven processes can take us to all of these different states in a controllable fashion. Okay, so that's the objective. This is the outline of what I'm actually going to say in the talk. I'm an experimentalist. We love fooling around with lasers, so I'm going to spend a little bit of time going through the tools of the trade. There are many different ultrafast techniques that we could talk about, but two that are important for this talk are transient absorption spectroscopy and two-dimensional electronic spectroscopy. So I'll spend a little bit of time talking about those. And then I'll just go through these three different dimers, which have three different kinds of behavior, even though the couplings between them are broadly similar. Most of these have dipole-dipole coupling with, in this case, moderate amounts of charge transfer coupling. Transient absorption is a technique which is very well established in the area of ultrafast spectroscopy. It all starts out with a short pulse laser, usually amplified to give us higher energy and a reduced repetition rate. So in our case, this is a 100 kilohertz source of 100 femtosecond, 800 nanometer pulses. And there are about a few millijoules per pulse. We use those to drive two optical parametric amplifiers, and that gives us a tunable output, typically with, in this case, 100 femtoseconds, and in this case we can go as low as maybe 20 femtoseconds. So we can do ultrafast spectroscopy on timescales longer than 10 femtoseconds if within our range, which is good enough for most chemical processes. The transient absorption itself, in this case we're using this laser here to focus that into a sapphire plate, and then sapphire plate undergoes a process known as self-phase modulation, which converts this actually near-infrared pulse into a broad white light continuum spectrum. And that we take through here, to our sample, which we use. So we use that as the probe, and eventually we spectrally disperse it. Sometimes we do polarization control measurements, and then we have both the parallel and perpendicular. But for most experiments, actually everything that I'll talk about today, we haven't made any use of this arm here. So it just goes here, and we measure a spectrum. The pump pulse can be essentially any color in the ultraviolet and visible region of the spectrum. We carefully delay that as a function of time. So we bring that in as our pump pulse. The pump pulse comes in, it excites our sample at the time that we choose to call time is equal to 0. And then this probe pulse comes in a controllable time later, the control being this delay stage here. And then we look at the transmission spectrum as a function of the delay time. And there's just one example shown here. I'll come back to this a little bit later on. This is one of the dimer examples. But you can see, here we get a negative signal. Okay, so this is something which has been removed from the sample. We refer to that as a bleach. So this has disappeared. We've got another negative signal here. This is a stimulated emission. So this is a molecule which has been formed in a fluorescent excited state, and our probe pulse has come in and stimulated the emission. That's the same as, that gives an increase in transmission, and so that has the same sign as a bleach. So stimulated emission and bleaches are negative, and these are new things that have been formed as a function of time. So these are positive transients, indicate products as a result of the pump pulse excitation. And in this case, we can probe across essentially the whole of the visible and into the near infrared region of the spectrum. That's the region where we can observe dynamics associated with the initial photoexcitation. So it's what we're observing, let's go back. It's what we're observing here as a function of time. You can see there's a change in the absorbance here and here as a function of time, and then if we wait for a long time, this eventually disappears, comes back down here. So those changes in intensity indicate a change in population. So a state is being formed here, and then it's relaxing and disappearing over here. Straightforward chemical kinetics. In addition, on top of that, we sometimes observe these things which are referred to as coherences, or vibrational coherences, or vibronic coherences, multiple names. And so here's the population dynamics down here, and then these coherences are these oscillations which are often observed for the first couple of picoseconds in a transient absorption experiment. And these arise from vibrations in the molecule. So these are coherently excited vibrations where if we have a displaced normal mode between the ground state and the electronically excited state, so this is a displaced anharmonic oscillator shown here. If the frequency associated with that vibration is, let's say, well, we worked one out earlier, so about 100 wave numbers, then that would take about 300 femtoseconds to oscillate backwards and forwards across there. If we bring in our 20 femtosecond laser pulse and we take our population from here up to here, then that is not enough time to populate that entire wave function. So what we're doing is launching a wave packet, so-called. We're taking this population here and we're putting it up on the left-hand side, the repulsive side of this potential surface, and it's going to oscillate over here, backwards and forwards. Right? We're going to launch a wave packet, and it's going to move in this direction and come back until the phase relaxation has killed that signal. And so that corresponds, if you see, this is the emission on the blue side of the spectrum. As it progresses across here, the emission is going to go to the red side of the spectrum. So as that happens, the total emission spectrum, or the absorption spectrum, but in this case the emission spectrum, is going to oscillate backwards and forwards in time. If this is the MG axis along here, along the table, it'll oscillate backwards and forwards in time. If we look at one particular wavelength, then that's going to correspond to an oscillation in the intensity. That's what we're seeing here. That's the oscillation in the intensity. Here it's on top of the population relaxation. We can remove the population relaxation, fit it to exponentials, and what we're left with are these oscillations here. If we Fourier transform those oscillations from the time domain into the frequency domain, then that gives us the spectrum associated with this vibration, in this case in its excited electronic state. So it's a way of getting vibrational information about excited states. Okay, we'll be coming back to those oscillations later on. This is a slide very familiar to Ismail. This is a two-dimensional electronic spectroscopy. It's a complicated, difficult experiment. It's principally difficult, well, one, because you have to deal with 4 different pulses, and worse, there has to be a complete phase stability between them. So it's not just enough to have the amplitude stability, also you have to have phase stability. That presents several difficult experimental challenges. They were overcome in this arrangement here. I'm not going to go through the details of it, but we have a single pulse coming in from our 20 femtosecond oscillator, and then it gets divided into 4 different pulses, all of which are have precise temporal and phase control over them, and they get focused onto our sample. So pulses 1 and 2 are separated by a time delay tau. Here I'm referring it as the excitation delay. And then we have a population decay between 2 and 3. Typically, this will be a delay of 0 to 1 or 2 picoseconds. This can be from 0, I think the longest I'll show is the 600 picoseconds. And then we have this delay here, which is the same as this delay here, and that's the local oscillator form. So these 3 pulses combine together in the sample over here, they're co-focused into the sample, generate Pi3 signal, a non-linear optical signal, which will propagate in the same direction as the local oscillator. Because they're in the same direction, then we can interferometrically detect that signal by interfering it with the local oscillator, and then we detect that interference in the frequency domain on our charge coupled device over here. And as I said, this experiment's really hard. Ishmael built all this, I didn't do any of that. But we did publish a paper together where we described this, and people still come up to me at conferences and say, oh, that paper was really helpful. We used that to build our system. And so I let them thank me, and I let them buy me a beer, but I didn't do any of that. Ishmael put this together, and it really is a really first-class instrument, which we've now given to somebody else to try to do something a bit more complicated, which I'll come back to later on. But why would you go to all this trouble? Well, if we have 2 states in a molecule, and that's just the spectrum, we don't know anything about them. We don't know if they're coupled or not. Well, you know they're coupled here because I've drawn those arrows. But generally speaking, you don't have that information. If we do a transient absorption experiment, then what we will see is all of this stuff collapsed into one dimension. And that dimension here is the dimension that we're measuring over here. The extra dimension comes about because of this time delay here. And if we Fourier transform over that time delay, then we end up with what we call the excitation axis shown here. So we're spreading our transient absorption spectrum out along the excitation axis. And that has a number of important consequences. One of which is if these 2 states are indeed coupled, then we will see that coupling as crossbeaks shown here and here. And that information would, of course, be completely lost if we didn't have that extra dimension. So we can reveal these couplings, and I'll show you several examples of those as we go ahead. In fact, I'll show one. What to say about that? Well, okay, no, this is even if we don't have these crossbeaks, we still always get new information in a 2-dimensional experiment that we can't get in a 1-dimensional experiment. This is an important molecule, chlorophyll A in solution. It's not a dimer, so it's not particularly relevant. But it's what you'll notice. It looks sort of the same as we go through here, but if you look a bit more closely, at early times it's elliptical, and as we go to later times it becomes more and more circular. That's because this axis is the inhomogeneous broadening of the system, and this axis, the orthogonal axis, is the homogeneous broadening of the system. So this is starting out inhomogeneously broadened, but as time goes on, that part of that inhomogeneous broadening is because of the orientation of the solvent molecules around it. They're dynamic. So as they move, what we see is that this becomes increasingly homogeneous. And so we can see this evolution from inhomogeneous to homogeneous grid on the timescale actually of the solvent dynamics. So here, the black point is showing the angle at which this is twisting. So here it's projecting just along the diagonal here, and here it's more in this direction. And you can see that the calculation fits it perfectly. I think there were quite a lot of free parameters in that calculation. But it allows us to observe this evolution from homogeneous to inhomogeneous broadening, which again you cannot do without doing a multi-pulse experiment. So it's an important tool. This is just an example that I just like to show, really. This is looking at the evolution of a crossbeam, which turns out to be molecular vibration. So we're just sitting, this is the complete duty spectrum, but we're looking at now multiple capital T time delay points. And what you can see is an oscillation at a wave number of 380 wave numbers. So that's actually associated with some a vibration around here, which is coupled to the electronic transition. And that's why we can see it in this electronic spectrum. So you get the frequency, and you also get the dephasing time of that vibration. So it's a really cute experiment. We can do a bit more with that. So it's what we've just done. Here's our, get this right. Here I've switched around. Here's the detection frequency. Here's the excitation frequency that we get from the Fourier transform. So that's one two-dimensional spectrum. And then we record lots of two-dimensional spectra as a function of that waiting time, capital T. So we record them in this direction, and what we've just looked at is looking at just one point here through many capital T measurements. And so we saw that oscillation, and if we do the Fourier transform, we get the frequency and the line width. But of course, we've done it here, but we can do it at any point over here. And in fact, we can do it at all points here. And when we do that, we create what's called a beat map. So for example, if we specify, if we do all of that, and then we look at the particular frequencies shown here, then we'll see that this occurs at this point where we just looked, but it also occurs again at this point. And so if you do that in the same real molecule, so this is that porphyrin that I looked at, here you can identify, and now we're specifically looking at this beat map at 375 wavelengths. You can see that there's a signal there, a signal there, a signal there, and a signal there. In this particular positive rephasing plot, as we call it. The details of this don't matter, but there are lots of different ways of breaking down these 2D spectra. But the difference between this one and this one is we can see the excited state with the ground state vibrations. And so in this case, there are two spots here. We can compare those with theoretical predictions. Each one of these spots corresponds to one or more of these pathways of excitation, where we're essentially pumping here and here. We have a broadband spectrum, so we pump here, probing over here, and this is our signal. And so this one is associated with one of those. I don't know which one. No, I've forgotten which one it is. But so because we can work out what all these possible pathways are for this four-level system, then we can theoretically predict where they should be, and we can compare them with experiment. And that is something that works perfectly. So that's very satisfying to see. But I'm just going to go on to explain a new version of that. And so why did we make such a perfect experiment and then give it away to somebody else? It's because there's a problem. We're a chemistry laboratory. And the experiment we've just done is this one, where we start out with this narrow absorption spectrum of the porphyrin, where we have an absorption here and a vibronic absorption here. That's that spacing there is our 375 wave numbers. And here on this side, we have the stimulated emission. To properly observe the spectrum that I've just shown you, our bandwidth has to be large enough to cover all of those transitions in one go. With our short pulsed NOVA, 20 femtoseconds, then we can do that perfectly well. Now I look at an important chemical problem. So this is a dimer system. I'm not going to show you this dimer system, but this undergoes a charge separation reaction. I'll show you another one later on. But look at the nanometers here. Here, that's about 60 nanometers. Here's our pump. This is where our absorption occurs. Here's the first transient absorption. Here's the second transient absorption. 600 nanometers. To get to 600 nanometers, we need a 3 to 5 femtosecond pulse. The bandwidth has to be huge to cover all of that. And in our laboratory, we just can't do it. We've got friends who can do it, and so we've let our clever experiment to combine with their clever laser, and at some point in the near future, we hope we'll get some results. Okay, so but essentially, we need a larger bandwidth if we're going to observe these interesting chemical phenomena. Here's an actual example of the disappointing result that we can get from 2D spectra, if you like. Simple dimer system here. This absorbs the energy, and it transfers the energy to this porphyrin. So this could be one of these light harvesting complexes, for example, that I mentioned earlier. And we can see that happening in the electronic spectra. So here are the two separated spectra. Here's the combination, and we excite this subthalocyanine absorption here, but we clearly see the emission from this porphyrin. So the energy transfer has clearly happened. We want to know the dynamics of that energy transfer. So we come along with our 2D experiment, and we do just that. And we can see it. I mean, it's not that this experiment failed, because you can clearly see, as a function of time, this signal here is appearing. This is as a function of the waiting time. So this is over this is 10 picoseconds. So we've seen the energy transfer happening. But it's really hard to pick that out from this spectrum and be sure what's going on. And the reason for that is our bandwidth in this experiment just covers this region of the spectrum. So we have to excite, so we're stuck around here. And so is what we're looking at with this time dependence here, a small changes around here. This is the dimer spectrum shown here. And that's all we can do, because that's the limit of our bandwidth. If I take that away now and do a transient absorption spectrum, it's obvious what's happening. I can clearly see this state, the subthalocyanine excited state, is disappearing as a function of time. I can see this state, which is the transient absorption of the porphyrin excited state. I can see that appearing as a function of time. So kinetically, the transient absorption spectrum is helping me much more than the 2D spectrum. So what I need is a 2D spectrum that at least covers this range in the detection. And that's what. Okay, there are two ways we can do that. The first one is the one I've already mentioned, that we give our beautiful experiment to people who have got a 3 femtosecond or a 5 femtosecond source. And this is not ours, this is from Tobias Brixner's group, but you can see that you can make these very broad pulses using what are called hollow core fiber systems. You put as you've already used, you put a short pulse in one end, and you get a white light spectrum with a short pulse out at the other. That is a potentially beautiful source for 2D electronic spectroscopy that we hope to get working in a little while. But in the meantime, in my laboratory, Giovanni Bressan, a student who worked with us and who's now a postdoc, has built this system, which is referred to as a half broadband two-dimensional electronic spectrum. So the broadband half is where we take our 800 nanometer pulse from our laser, we focus it into, where is it? Oh, here. we focus it into our sapphire plate, then the self-phase modulation gives us a white light continuum, which is a bit of a messy white light continuum, but we can tidy it up, we can compress it into a very short pulse with these church mirrors. And that goes all the way around here, and it becomes a probe in our sample. Up here. Where's the sample? And the sample's up here. Okay, so that's our probe. Our pump, if you like, comes from our short pulse NOPA again. That then goes through an acousto-optic modulator, which can do a lot of things, but one of the things it can do is split that single pulse into two pulses with a phase control delay time between them. So this is now going to be the pump source, which is giving us pulses 1 and 2, and our white light continuum is going to be pulses 3 and 4, the local oscillator. So then this comes, so the one delay time is given by our modulator here. The pump probe delay time is given by our long delay stage here. And we can combine everything together in this simple two-beam pump and probe geometry. So here's our pulse sequence again. Here's our pump delay time, and here's the long probe delay time. And so when we do that, this is just an example from a dye that we've been looking at. We can see the ground state signal shown here, which is all we would see with a narrowband NOPA. But because we have this broadband white light continuum probe going along this axis, then we can also see the excited state absorption. And so we can go and look for our coherences. For example, we can look here and look here for these coherent oscillations that we've seen in the earlier dye. And here they're shown. This one is in the ground state, and there's a single mode dominates at around about 550 wave numbers. If we look on the same excitation axis, but in the excited state absorption, then we see at least two signals. One at 380-ish, and one at, again, at around about this 550. And you can see that there are two signals there because the time domain signal is beating one against the two modes are beating against each other. So then we can make our beat maps of this, and as you can probably guess, the 585 mode, not 550, 580, appears actually dominantly in the ground state, but also appears in the excited state. Whereas our 350 mode appears only in the excited state. So this is telling us about the structure of our electronically excited states as we go from S0 to S1 up to Sn. Detailed analysis of this is complicated, but what it allows us to do is calculate reasonably accurately the displacements between S0 and S1 and S1 and Sn. And this is new information again, which we would not have been able to get if we did not have this broadband probe. So this broadband probe is, I believe, a useful advance in two-dimensional spectroscopy, but intermediate on the way to having a full broadband spectrometer, which we hope to have in the near future. Okay, let me talk about some diamonds, getting towards the end of the talk, but here's an interesting one. This is the dimer of porphyrins connected by this alkyne bridge. It's actually the fundamental unit of an important set of molecules, which Ismail may have talked about here, these porphyrin rings. But this in itself is interesting because it exists in two forms in the ground state. Planar form, which absorbs here, and then at slightly higher energy we have the twisted form. We know that's true because our clever chemistry friends have made a ligand which forces this to be planar, and when we add that ligand then we see that this band shoots up, this band shoots down, and so we know that that is the planar form of the dimer. Okay, well, if we study that with two-dimensional spectroscopy, we see lots of interesting coherences. We've seen them before, so they're not so interesting to us anymore. They're exactly where we would expect them to be. What's much more interesting is what happens if we look on a long time. And I'll show you that. If we just focus, first of all, down here, you started out stretched out here, inhomogeneously broadened. But you can see we're getting population appearing here. So in the first few tens of picoseconds, we're filling up this cross peak here. And that goes on and on and on for, we're at nearly 100 picoseconds now, so this is like archaeology for ultrafast spectroscopy. But then focus on what happens up here. As we head towards 600 picoseconds, and this top quadrant, this cross peak here, starts to fill in. Again, this is all information that you can only see in two-dimensional spectroscopy. That's the movie. If we just look at those 2 points here, then this is the down here. This fills up quickly, a few tens of picoseconds, and then it decays away again. Whereas this upper cross peak here fills up and just keeps filling up over hundreds of picoseconds. So we can analyze this and see what's going on kinetically, and it's actually fairly straightforward to explain. When we bring in our broadband pump pulse, we excite both the planar form and the twisted form of the ground state, because they're not so far separated in energy. In the ground state, this is a bit more stable, but there's a thermal population of both the planar and the twisted. In the excited state, this one is a lot more stable. So any population that was in here is going to transfer to here. And that's why it appears cross peak. There's the high energy, there's the low energy, the cross peak is coming here. Okay, so we can understand where that behavior is coming from. But now I think we've put this in the excited state. This population has now pumped over to here, and then it's gone back to the ground state. So now we've got an excess of population in this state. And what you're looking at here is the re-establishment of this thermal equilibrium in the ground state. We can see that that takes hundreds of picoseconds. So it gives us quite a nice insight into the kinetics of this kind of excited state and ground state. This is a second dimer system I want to introduce you to. We saw some of the data a little bit earlier on, but this is a subphthalocyanine dimer. So here's the monomer, and it's got a really simple behavior. It's shown in black here. That's the monomer absorption. That's the monomer emission. Classical allowed transition behavior. When we make the dimer, you can see that we get a rather distorted spectrum, and we get both a red shift and a blue shift in the spectrum. That's because if you look at this, there's a linker molecule here, a linker atom here, and that's an oxygen atom between these two borax. And that oxygen atom means that the dimer is not like this, but it's like this. And if it's like that, then both the upper and the lower parts of the excitonic coupled band are both optically allowed. Therefore, we get both a blue and a red shift in this one. And the emission spectrum of the dimer is now rather far. This is in toluene in a non-polar sign. Rather far to the red. And this is the case of this X-imer coupling. So this is very characteristic of X-imer formation, where we have this charge resonance coming into play. And that's because these are really quite close together. But we've got some degree of wave function over them. So this is what we see in these non-polar solvents in the transient absorption. So this is the ground state bleach. And on a time scale of 0 to 10 picoseconds, nothing happens to the ground state bleach. Population's gone to the excited state. And it's what we see is instead the formation of this stimulated emission. Stimulated emission is coming from the excimer. So what we're looking at here is the kinetics of this excimer formation. So this excited state is undergoing some kind of structural motion. We don't know exactly what it is, some kind of twisting motion, which is allowing this excimer to form in a couple of picoseconds. And that's accompanied by a new absorption out here, and that's a characteristic, actually that's a characteristic dimer band, which is a coupled dimer band, which is being formed. Interesting thing is, if we put this in a polar solvent, then we kill that fluorescence. Stone dead, it's just gone. But that doesn't mean everything becomes very fast. It's not just returning to the ground state. It's what we see is no stimulated emission now. It's actually going the wrong way for stimulated emission. And the dominant behavior here is an increase in absorption on the ultraviolet end, the high energy end of the spectrum. And we can trace that actually by chemical manipulation, by oxidation of this state here. We can trace that to a charged form of the dimer. So as what we're seeing in a polar solvent is a charge separation reaction. So this, we're putting this into an excited electronic state. It's forming an excimer in a non-polar solvent, but it's symmetric. We don't really expect it to then form a charge separated state. But of course, we put it into a polar solvent. The polar solvent can transiently apply, if you like, apply an electric field to that excimer state, and that then favors the formation of the charge separated state. And we can do a little bit better than that, because we can look at it. We're looking at it in a solvent called dimethylformamide. Dimethylformamide has some dielectric relaxation dynamics which are actually well known. So we can compare the rate of our excited state reaction with the dynamics associated with dimethylformamide, and the thing which is driving this charge separation, we can prove, is the solvent dynamics. The solvent dynamics about that excimer, converting the excimer into this charge separation. So this is just a cartoon of that process here. So we come here and we form quickly the excimer state, but in a non-polar solvent we can't access the charge separated state. The non-polar solvent is not polar enough to stabilize it. But as we move to a polar solvent, then we can have a transient electric field applied to our excimer, and that can then stabilize this symmetry breaking charge separated state. We've also looked at this in two-dimensional electronic spectroscopy. We're still analyzing those data, so I'll skip over those just to finish nearly on time and show you this final dimer, which is, I want to talk about, we're still discussing the analysis even today about what we think is going on, but it's such a beautiful construction. The chemist in the audience will no doubt appreciate this. Because if you look at that, these are two parylene diamides which have been manipulated to have an almost exactly parallel stacked structure. And these linkers here are really quite rigid. So we thought if we worked on that, we would know exactly what structure we were working with. And that's very difficult with these diamides. And the interesting thing about this one is that even though we thought the structure was the same, if we change the solvent, we get very different behavior. So in green here, I'm just showing you a monomer of the parylene diamide, shown here. If we look at this in a slightly polar solvent, tetrachloroethylene, trichloroethylene, slightly polar solvent, then we see essentially the same thing. But if we look at it in toluene solvent, then what we see is a very classical H-type exciton coupled dimer. Right? Here we have a blue shift. We don't see no fluorescence, as what we see is a redshifted fluorescence. The redshifted fluorescence is quite characteristic of an excimer formation. Because what we think is probably happening here is that in the toluene solvent, these two are coupled, and then that is forming an eczema once it gets the electronic excitation. Okay, so there must be some coupling between these two species, which is somehow being turned off by the polar solvent. There's a theory due to Spano which applies very nicely to these Parylene systems, which is based on the ratio of the 0 to 0 compared to the 0 to 1 transition. And so we can work out the strength of the coupling in these two solvents. In the polar solvent, it's about 160 wave numbers. In the non-polar solvent, it's about 610 wave numbers. So much stronger coupling in the non-polar solvent. So if what we believe now is happening, there are a couple of possibilities. But we believe that actually this structure is changing in the polar solvent. Because it can't move in distance, but if there are some hydrogen bonds which are formed in here, and those can be broken by the polar solvent, and that allows the top half to twist slightly with respect to the bottom half. And if it does that, then this charge transfer contribution, which I talked about, this contribution to the wave function overlap, that can change. And we think that that change is sufficient to drive, or to kill the coupling between these two molecules. So these are basically at a critical distance where a small change in the coupling is enough to effectively turn off the interaction between the two layers. And we can control that by the solvent. Two-dimensional spectroscopy. Okay, now this story goes forward in a pretty straightforward way. This is the monomer. This is the uncoupled dimer. And they look pretty similar to one another. They're effectively identical. The coupled dimer is extremely different. So we kill the emission, so the stimulated emission is gone. What we see in place of it is a transient absorption, which is associated with the eczema. If we look at that in real, so this is a two-dimensional spectrum. If we look at that in real time, we see these oscillations, but nothing else in the monomer or the uncoupled dimer. In this state, we see on a timescale of 150 femtoseconds the formation of the eczema. So we can extract the formation of the eczema kinetics as a function of time. And that formation in the toluene solvent, in the non-polar solvent, is extremely fast because they're held in the right position for that to happen. Okay, so we're still arguing about the interpretation of these. The key thing to notice here is that, once again, this low-frequency spectrum, very characteristic of the monomer or the uncoupled dimer, it changes a lot when we go to the eczema. There's some new low-frequency spectrum which is appearing here in the eczema. And we can play a trick called the windowed Fourier transforming, which is essentially looking at the temporal evolution of those frequencies. So we can look at the evolution of these spectra as a function of time. Not straightforward, there are tricks associated with this. But you can see that these don't do very much with time. A little bit of something here perhaps in the dimer, but not very much. Whereas in our coupled dimer, we can see that this mode starts out at about 160 wave numbers, 170 wave numbers, not so different to this one. Then it evolves in time to the higher frequency where it apparently ends up. And as a function of time, in the first 300 femtoseconds, these modes appear. So these modes appear to be specifically associated with dimer formation. And interestingly, possibly interestingly, yet to be proven, that this is a reaction where the coherence is surviving. So we're getting a chemical reaction, we're going from a neutral state to an eczema state, and the coherences are surviving, which is unexpected. Okay, so let me finish. Some general conclusions. This combination of two-dimensional spectroscopy with transient absorption provides new insight into dimer coupling and the dimer reaction dynamics. Lots to be learned, lots more to be learned, I think, from these techniques. We can see solvent-sensitive low-frequency modes in dimers. Indeed, we can see that the solvent allows us to control the nature of the final state in these excited dimers. Solvent control, as I just said, solvent controls are powerful route to controlling the electronic structure. What we don't know is how to predict that so far. We thought we knew with this Perylene dimer that we had shut down all those pathways and that it would be a well-behaved dimer, and it turned out that the solvent could completely switch it off. So. And these beat maps reveal new information, but their analysis is complete. Let me just stop with thanks to, this was a picture taken when Ismail was in our laboratory, I'm afraid, 10 years ago. Still looks young and energetic. Giovanni for the two-dimensional broadband experiments. Dale did the theoretical simulations, a lot of work I didn't have really time to talk about. Palas did the subphthalocyanine transient absorption measurements, as well as a lot of time resolved Raman, which I don't have time to talk about. But with spectroscopists, if we want to do something interesting, then we have to have interesting things to work on. That's critical, in my view. So we can't make molecules, but these guys can. So Harry Anderson made the porphyrin dimer and many other porphyrin complexes for us. Andy Camage made the subphthalocyanine dimer. He's a colleague at the University of Anglia. And Tim Barrett is a very bright young scientist at Birmingham University, who made that pink box dimer. And I called him up and said I wanted it, and he was kind enough to send it to me. So these guys were vital in our work. We can't work without them. Can't do interesting work without them. These people put up the money, and I thank you for your attention. Questions? Happy to take questions.
Yes. Sorry. You were to change the big box example, the distance of the how it linked from one to the other.
Yeah. No, it would be great if we could to change that, but then I have to be very nice to Tim, because that's actually synthetically quite a difficult thing to do, because the further apart you make them, the floppier they become, so they have to do something else to rigidify.
Yeah.
But these kind of control elements, things that we dream about, and of course, if we could understand properly the mechanism which is driving us to this maybe useful charge-separated state compared to maybe a useless excimer state. If we can say, okay, we understand that and we can predict that following structure will give us the following result, then somebody's going to go and make it. But if I just call them up and say, hey, why don't you change this? And they'll say, well, maybe that's 2 years' work. So is it going to be worthwhile? So I think that as we understand more about features that control these dynamics, then we'll be able to ask for more synthetic examples that we can play with.
Now that your comment is said, the excimer is sort of useless, if I understand. So could you comment, is that really the case? I mean, is the excimer something you want generally in the community, or is it something you want to avoid in the structure?
I believe that the excimer will always, is likely to be a route to the charge-separated state. So I don't say it's necessary to go through the excimer, but I think the eczema is a very good probe of, if you like, the initial stages of the coupling. So having more examples where we can see the eczema is nice. Examples that we've looked at so far show that we can go from the eczema to some kind of charge-separated state. Again, doing that predictably. Ideally, where we didn't have to have the solvent do it for us, where we could do it in some kind of, maybe some macrocycle would be nice. But yeah, I think the exome is interesting, but it's an interesting intermediate onto something else.
Any more questions? Oh, yeah, let's thank the speaker again.
It's not for that.
Return.
Yes.